In today's world, we rely on computer models to help us learn about and respond to many types of complex systems. For example, models of traffic patterns help us to time traffic lights and to design new roads. Models that simulate airplane flight help pilots learn how to fly. And models that simulate Earth's climate help scientists to understand past climate and project future climate. But just how are these models constructed? Because Earth's climate varies from place to place, modelers start by dividing up Earth's surface into smaller boxes, or grid cells. Typical climate models have grid cells that are about the size of the state of Connecticut. It takes about 35,000 of these cells to cover the entire surface of Earth. You can think of the grid cell as the smallest unit in any climate model. Let's take a look at what goes on within one of these cells. Each grid cell has information about whether it is covered in land or ocean, and the proportion of each. More sophisticated models include detailed information about what is on the land, including mountains, farmland, forests, and cities, and also the characteristics of the ocean in a given location. Within each grid cell, climate models then simulate the movement and changes in air, water, and energy. These processes are based on the laws of physics. For example, this equation is used to calculate the pressure in the atmosphere. This equation determines changes in the sun's energy, and this equation calculates the speed of ocean currents. These equations are then translated into computer code. A climate model is the sum total of all of this computer code. But climate models are much more complicated than what we have discussed so far. Things in the real world change in time, and processes in one part of the world affect things in other parts. These processes need to be tracked in both space and time. We break down an example of air motion into 3 time steps. In our first time step, observe the wind and how it would be expected to flow over the mostly flat land area in the grid cell on the left. In the second time step, the air moves into the next grid cell and is forced up and over the mountain range. In our third time step, the water vapor in the air condenses into a cloud and rains on the city below. In addition, models also incorporate processes happening in the ocean, processes related to radiation coming in from the sun, processes related to glaciers, and processes related to human activities. As you can see, even within a single grid cell, there are many factors to consider when modeling something as complex as Earth's climate. When we scale this back up to the size of Earth, where we need many thousands of these grid cells, it becomes clear why supercomputers are often needed to run these simulations forward. In the end, we get a climate model that ties all of these processes together to simulate Earth's climate. Here are some examples of various models in action. This model shows global surface temperature. This one shows global cloud cover. Other models show Arctic sea ice and ocean temperatures, ocean currents, or atmospheric circulations. Demand for the information for climate models keeps growing as farmers, water managers, city planners, and many others look to respond to a changing climate.